Good day, everyone. So we are reviewing Wetzel's Limnology textbook. This is edition number 4. We're on chapter 15, the phosphorus cycle, and more specifically, we are looking at phosphorus cycling in the epilimnion today. And we are starting with soluble APA and APA associated with algae and non-algal particulate matter are highly variable seasonally and spatially. And just a reminder, APA is alkaline phosphatase activity. Epilimnic APA is commonly high during the spring and summer periods of maximal phosphorus demand during years when spring circulation is incomplete or a lake experiences temporary marrow mixes. Extremely high APA and phosphorus limitations were found in the phytoplankton during spring and summer months. Phosphomonoesters PME were found in lake water in substantial quantities, up to 55 micrograms of PME or phosphorus per liter in eutrophic Twin Lakes, Ohio. An inverse relationship was found between PME and concentrations and APA during summer stratification. Potential hydrolysis rates of PME greater than 0.05 millimoles per hour by APA were found. These values are similar to those found in marine systems using algal alkaline phosphatase as the hydrolytic enzyme. These results, in addition to widely differing chemical analysis of the complex phosphorus pool in lake water, suggest that the composition of the soluble phosphorus pool varies greatly among different lake types. Although some lakes may approach the model of phosphorus cycling presented in figure 15-10, other lakes may possess a phosphorus cycle dominated by the production and biotically mediated hydrolysis of PME. Physiochemical mechanisms can also influence the cycling of phosphorus and as a result affect primary productivity. Certain complex humic materials of both low and high molecular weights contain phosphorus, such as phosphate esters and inositol hexaphosphate. High molecular weight humic compounds can be photoreduced by low intensity ultraviolet light as occurs in sunlight. Orthophosphates adsorbed 2-ferric humic compounds can be released by UV-induced photoreduction of ferric iron. Low molecular weight humic compounds can release orthophosphate upon exposure to alkaline phosphatase. Phosphorus humic complexes can interact with phytoplankton and bacterioplankton in complex ways. For example, rates of carbon assimilation by phytoplanktons were reduced when phytoplanktons were exposed to low concentration of dissolved humic materials of littoral and wetland origin. The effect were species selective and greatest among smaller, between 1 and 5 micrometers, phytoplanktons growing under low light conditions. The production of alkaline phosphatase activities was greatly stimulated by low concentration of dissolved humic compounds of low molecular weight. Evidence indicates that these humic materials can act as sequestering agents for phosphate ions, organophosphorus compounds, and iron, thereby reducing phosphorus and possibly iron availability to phytoplankton. These relationships can be important to both phosphorus cycling and phytoplankton productivity from major rain events, can simultaneously introduce substantial quantities of phosphorus and dissolved humic materials into the pelagial areas of small and moderate-sized lakes. Additionally noteworthy is that in acidified lakes where aluminum Al3 and iron Fe3 concentration can be markedly increased, the production of acid phosphatases is enhanced, although the Al3 and Fe3 at low pH do not affect the enzyme directly. The metal ions combine with the phosphate groups on the substrate and inhibit enzymatic hydrolysis. The organisms may compensate at considerable energetic cost for these losses by increased production of phosphatases. Phosphorus losses by outflow, inactivation, and sedimentation. Accurate nutrient budgeting in a lake or river ecosystem requires quantification of routes of reduced availability for utilization by biota, as well as direct losses. Direct losses by movement with water in outflows from lakes and rivers occur in inorganic and organic dissolved and particulate forms. Knowledge of concentration and discharge volume allows reasonably accurate evaluation of losses by outflow. Losses by seepage through the sediments, particularly as sediments near the shorelines, are quite variable. However, in most lakes, the basin seal is relatively complete and seepage outflows are small in relation to surface outflow. Most of the losses of phosphorus by seepage are via dissolved inorganic and organic compounds. Sedimentation of nutrients occurs in settling A, living and dead biota, and B, inorganic particles that are imported to the water from the catchment or are formed within the water and absorb nutrients. As particles settle to the bottom, they can experience partial decomposition and microbial recycling of nutrients to the water or encounter altered chemical conditions that change nutrient-absorptive properties of the particles. Once at and within the sediment, periodic resuspension occurs, especially from superficial sediments in shallow waters. Major resuspension occurs at times of complete water circulation, during which several centimeters of the superficial sediments can be suspended into the water column. Most surface waters of the world are bicarbonate dominated, and many, perhaps a quarter of them, lakes are very hard waters with sufficient bicarbonate and calcium to experience periodic precipitation of calcium carbonate. Precipitation is induced and accelerated by high pH, and these conditions are often associated with macrozones adjacent to rapidly photosynthesizing cells of the phytoplankton, attached algae, and submerged macrophytes. Sedimentation of nutrients occur in settling A, living and dead biota, and B, inorganic particles that are imported to the water from the catchment or are formed within the water and absorb nutrients. As particles settle to the bottom, they can experience partial decomposition and microbial recycling of nutrients to the water or encounter altered chemical conditions that change nutrient-absorptive properties of the particles. Once at and within the sediments, periodic resuspension occurs, especially from superficial sediments in shallow waters. Major resuspension occurs at times of complete water circulation, during which several centimeters of the superficial sediments can be resuspended in the water column. Most surface waters of the world are bicarbonate dominated, and many, perhaps a quarter of them, lakes are very hard waters with sufficient bicarbonate and calcium to experience periodic precipitation of calcium carbonate. Precipitation is induced and accelerated by high pH, and these conditions are often associated with macrozones adjacent to relatively photosynthesizing cells of the phytoplankton, attached algae, and submerged macrophytes. Much of the phosphorus associated with the calcium carbonate is adsorbed onto the crystal. A small portion is incorporated by co-precipitation into the growing meat as crystals. Inhibitors of calcium carbonate growth, such as magnesium and iron, induce the amount of phosphorus co-precipitated on calcite. The morphology of calcite crystals can change markedly under different environmental conditions. In particular, the complexity of the crystals increases with increasing supersaturation, and they shift from rhombohedral to complex dendritic and columnar crystals. As the crystal complexity increases, the adsorptive surface also increase and are potentially more effective in the removal of nutrients and dissolved organic compounds. Because phosphorus is co-precipitated with and absorbed to nucleating calcium carbonate, the process of formation and sedimentation of calcium carbonate can markedly alter phosphorus availability to biota. For example, about 35% of the annual total phosphorus removal from the epilimnion of Lake Constance in southern Germany was associated with autochthonous calcite precipitation, some 25% in eutrophic Wörthersee of Austria, and about 30% in hypereutrophic Onondaga Lake of central New York. In hypereutrophic prairie lakes, very high concentration of phosphorus are stripped from the epilimnictic waters by periodic precipitation of calcium carbonate. In hypereutrophic prairie lakes, very high concentrations of phosphorus are stripped from the epilimnictic waters by periodic precipitation of calcium carbonate. Phosphorus and nitrogen uptake and recycling by protists and zooplankton. As we have seen, the phosphorus content of bacteria is about 10 times that of algae. Bacteria are commonly responsible for 80% or more of the net uptake of phosphorus. Thus, bacterial plankton are a potentially rich source of phosphorus. Many studies have examined the ingestion of algal and bacterial particles by macrozooplankton and the potential regeneration of phosphorus by the feeding activities and from excreted feces, as discussed next. It should be emphasized that such uptake and excretion of phosphorus and other nutrients is a recycling process, not a de novo source of nutrients. The digestive and metabolic processes alter the storage time of the nutrients already in the ecosystems and potentially render them more available for reuse by other organisms. Where the uptake of and recycling by the heterotrophic microflagellates were compared to the large zooplankton, the heterotrophic flagellates feeding on phosphorus-rich bacteria regenerated 2/3 or more of the phosphorus released by grazers. Phosphorus and nitrogen regeneration rates varied, however, among fast and slow-growing species of the heterotrophic flagellates and were much higher during exponential growth phases than during stationary growth phases. A portion of the bacteria senesce and lyse and thereby release nutrients. However, many of the bacteria functions as consumers of phosphate because of their high requirements for phosphorus and thus serve as phosphorus-rich particles for feeding by flagellates, other protista, and larger zooplankton. The release rate of phosphorus from the bacterivorous feeding of flagellates can account for major recycling sources for phytoplanktonic primary production. This recycling by planktonic consumers can be a significant source for the growth of bacteria and phytoplankton, particularly late in the summer period of stratification during periods of low inflow. So let's look at figure 15-11 here. Calcite crystals from hard water lakes under different conditions of chemical saturation. Marked alterations of surface areas and absorption also occur with changing morphology of the sedimenting crystals. So increased supersaturation, and we're talking here of phosphate. It's increased in saturation, I believe. And it shows how the geometry of the calcite crystal changes depending on the concentration of phosphate. So this is before supersaturation, so it's pretty much a square, and you can see dendritic pattern with supersaturation, and this is shown here in this pattern. So increasing in complexity of the crystal as the supersaturation increase. And then here we have increased adsorption. So this is where the phosphate is actually like linking itself to the surface of the crystal, the calcite crystal. So we can see the growth of that phosphate onto the surface of that crystal. So we start with a very geometrically clean polygon here, and we end up with this polygon that has multiple layers of phosphate on top of its surface. And you can see the growth of that surface. So first it mimics the general pattern of the crystal itself, and then it starts a random pattern of crystallization here, and we can see that in the figure that is presented in here. The uptake of nutrients, particularly phosphorus and nitrogen, by ingestion of food particles by herbivorous zooplankton and protists can be large, and at certain times of the year. During ingestion and subsequent leaching from feces, nutrient release occurs in the form of soluble phosphate ions greater than 70% of dissolved phosphorus, ammonium nitrogen greater than 80% of dissolved nitrogen, and some organic phosphorus and nitrogen compounds, particularly urea, usually less than 10% of dissolved nitrogen. The release rates are highly variable, but the rates of nitrogen released from crustacean zooplankton range between 0.2 and 2 micrograms of nitrogen per milligram of dry weight per hour, increase with increasing food abundance, whereas the rate of phosphorus release 0.5 to 0.3 micrograms dry weight per hour, and nitrogen phosphorus release ratios were affected directly by the nitrogen phosphorus ratio of the food. Release rates of ammonium nitrogen were similar per unit biomass for ciliates and phagotrophic flagellates. When prey food organisms were saturated with phosphorus, release rates from grazing zooplanktons were in the range of 1.1 to 1.5 micrograms of phosphorus milligrams dry weight per hour. When planktonic bacteria and algae are phosphorus starved and contain less phosphorus, however, release rates from grazers are about 0.05 micrograms of phosphorus per milligrams of dry weight per hour, less than 5% of the rate under phosphorus sufficient conditions. Detrital particles were also found to contain very low concentration of phosphorus. Appreciable quantities of phosphorus, nitrogen, and carbon remain in the particulate fecal materials and dead zooplankton that settle out of the water column. Loss rates of nitrogen or phosphorus from molting or dead crustacean and waterifer zooplanktons were the most rapid during the first 24 hours following death. Thereafter, rates of nutrients and carbon losses decreased, but usually greater than 75% was lost in the subsequent 6 days. Release rates were somewhat faster in the warmer water strata than in the apolimnion. The quantitative significance of these sources of nutrients from micro and macro to zooplankton to phytoplanktonic productivity is unclear. Where examined carefully, zooplanktonic excretion of nitrogen likely constitutes only a few percent, less than 5% of that required for gross production on an annual basis. Recycling of phosphorus could be appreciably higher, particularly during certain periods of extensive zooplanktonic grazing. The difficulty is that very few quantitative measurements of rates of nutrients regeneration by bacteria, protists, and other processes have been examined simultaneously with the estimates of release from zooplankton. For example, in eutrophic Lake Loostrecht in the Netherlands, in the summer, less than 30% of the phosphorus required by phytoplankton emanated from zooplankton excretion. Most regeneration of phosphorus resulted from excretion and release from bacteria and algae. To ignore nutrient regeneration by rotifers and protists as insignificant is in comparison to cladocerans is not warranted. Although the individual biomass of the smaller organisms is less by 2/3 to an order of magnitude or more, densities are often several orders of magnitude greater than those of cladocerans. Specific excretion rates are generally higher as biomass decreases. Estimates indicate that microconsumer protists and rotifers can generate 50% or more of the total phosphorus and nitrogen that is regenerated by the total zooplankton community. And I think that's going to be it for today, and we'll pick it up tomorrow with nutrients released by zooplankton. And thank you for jamming in today and tuning in, and I'll see you tomorrow. Thanks. Bye.